Hello, everybody. Today we are going to understand and kind of prove it intuitively a theorem about a direct sum and isomorphism. So yeah, let's see what the theorem is talking. The abelian group A is a direct sum of subgroups B and C if and only if A equals B plus C and the intersection between B and C is the element 0. This is the case if and only if the map B Cartesian C maps to A given by BC maps B plus C is an isomorphism. So yeah, think for a while. It's not really complicated to understand what's going on. Direct sum is pretty intuitive. There's some cool properties about direct sum. The direct sum needs to be unique, and that's important because we're going to use injection property. If we think about a recursion function that maps a set A onto A, it needs to be a injection. Why? We're going to see. So yeah, let's see the case where B plus C is not equal A. So let's talking about sets now. B union C is different than A. So we have A, we have a subset B, actually a subgroup B, and a subgroup C. The intersection between them can be empty, only 0, or not empty, doesn't matter. So here for this case, there's some elements here on A that you can't combine both B and Y to get to this element. And you're going to ask why actually can't make this. So let's talk about two important groups that we see almost every day, and they are groups, and I don't know if you know, but it's if you don't know group theory, you won't understand. But I assume if you're seeing this video, you know pretty much the basics of group theory. And what groups am I talking about? Well, I can talk about a bunch of groups, but let me choose the largest ones. The complex and real numbers. Well, are they groups? Abelian groups? Yes, under addition they are, because real set is closed under operation, so law of composition is valid. It's abelian because yes, associative also because of yes, you can check it, but I mean it's pretty much defined to be associative. It's commutative, so it's abelian, right? And both are groups because they have the 0, which is the unity element of addition. So they are group under additions. Well, what's my point am I trying to make? Well, I'm trying to make that you can't write some complex numbers as a direct sum of real numbers. So for example, take a number that has a complex part different than 0. You can't. You can't write yourself. You can't write square root of -1 because it's not defined on the real set. Okay? So we verify it that this relation needs to be injective. Not injective, bro. It needs to be the union needs to be equal to the group, because if it's not, then there are some elements you can't write as a direct sum. And I showed the example of real and complex numbers. Nice. And now let's talk about the intersection. The intersection needs to be equal 0. Why? Well, the intersection on the first case needs to be 0, because if it wasn't, then you couldn't write 0 as 0 plus 0. Because imagine that the intersection is equal to some A, where A is different than 0. And okay, so if A belongs on B, I'm not gonna write implies, then A is not an element of C. And you could change B to C and see it. Okay, what's my point? My point is that I need to write every element as a sum of B and C. And so since 0 is on A because it's an abelian group and 0 is the unity element, and for example, let's consider that 0 is some BI. Okay, then this 0 is not some CJ. Some CJ. because, well, the intersection of them is not 0. So they don't have the elements. They don't have these elements, of course. If BI has 0, then CJ won't have it, because we defined it this way. So okay, we saw that it needs to have 0. But what about other elements? What happens when it has other elements? Well, when it has other elements, it's better. Because now, okay, we already showed that the union needs to be equal to the group, the larger group, in this case A. Let's consider that B union C equals A. This drawing is merely a representation of what I'm talking about. So okay, there's some element X that it's both on B and C, so you could write B, so you could write X as some 0 plus BY plus BI, and as some 0 plus CJ. And this is two complete different elements. Understand what I'm talking about? You're mapping 0 and C to a B, to an X, and you're also mapping some 0 and B to some X. And that's crazy. That's crazy because, well, it fails the uniqueness property, because now you have two ways to represent the same number, even though C and B is equal in this case. But yeah, it's a 0 and it's a B and C, and the C and B where, okay, it's 0, right? Okay, the uniqueness fails. So uniqueness needs to be unique. Now let's check why is it an isomorphism. What's an isomorphism? Isomorphism is a group that is bijective. So it's injective and surjective. We saw why it needs to be surjective, because if so you couldn't write the element, one element here as another element, right? And let's talk this. This is A and this is B, X, C. Would have some elements here that you couldn't decompose it, like take the inverse, because simply you couldn't write them. So B and C wouldn't be a unique sum, because there would have some elements on A that you couldn't write as a sum of B plus C. Okay, that's nice. So why does it need to be injective? Because of definition. Yeah, the direct sum is unique, and we saw what happens when the intersection is different than 0. You could have two different sums that map to the same element, right? That's what I'm talking about. Well, that's it, guys. I hope you understood it, and I hope you liked it, because yes. So yeah, it's an isomorphism relation. You just need to prove that it's an isomorphism relation. And if it is surjective and injective, then it's bijective, and so is isomorphism. That's it. It's not difficult, but it's a great understanding.